Okay, so this is where we left off, and we basically did this example on how can we figure out if a structure is aromatic or not. And I told you there were 4 rules, and right here are the 4 rules. It's got to be a ring, there's got to be a double bond or pi electrons at least with every atom of the ring. Number 3, it needs to be flat. And number 4, it has to have an odd number of double bonds. All right, so there's one thing on here that I want to talk about in more detail, and that is number 4. All right, so I'm going to clear this screen out just so we can start with a fresh, clean slate. And number 4 says something about an odd number of double bonds, or really pi electrons. I keep saying that because this is going to be a problem in the future if we just think double bonds only. It cannot just be double bonds, but that's what we see most of. All right, so odd number of double bonds. This is actually something called Huckle's rule. All right, so Huckle's rule was named after Mr. Huckle. And Mr. Huckle said, in order for an aromatic to take place, here are my discoveries in the laboratory. And it basically gave a summary of all of the things that these compounds had in common. And what he found out is that there was an equation embedded here, and this equation was 4n plus 2. And 4n plus 2, well, that n represents something. All right, so what that something represents is just basically n equals 1, n equals 2, n equals 3, n equals 4. So what Mr. Huckle discovered is that I could substitute 1 n for the n. So 4 times 1 is 4 plus 2 is 6. And then the 2 gets substituted. 4 times 2 is 8 plus 2 is 10. And then the 3 gets substituted. 4 times 3 is 12 plus 2 is 14. And then 4 gets substituted. 4 times 4 is 16 plus 2 is 18. All right, so I know that electrons form bonds, and I know that 2 electrons are needed to form a bond, so I'll divide all of these by a 2. And what do I get? All right, well, 6 divided by 2 is 3, and 10 divided by 2 is 5, and then 14 divided by 2 is 7, and then 18 divided by 2 is 9. Folks, this is a way that Huckle basically proved an odd number of double bonds exist. All right, he basically used this equation and said everything kind of follows this trend, and every calculation that we do on these compounds, we get an odd number. So aromatics have to have an odd number of double bonds, and it kind of originates from this equation. So here's a different example problem, and it says, what's the value of n in Huckle's rule when a compound has 9 pairs of pi electrons? All right, so I just told you what that equation was. It's 4n plus 2. So 9 pairs. Okay, 9 pairs of electrons. Pair is like a pair of socks, a pair of shoes, a pair of gloves. There's 2. Well, what about a pair of underwear? You don't wear 2, do you? That's kind of weird. Or a pair of glasses. You don't wear 2, maybe a pair of lenses and a frame, but 9 pairs. Okay, so 9 times 2 is 18. So 18 is equal to 4n plus 2. I subtract 2 from each side. We're going to be in a math class. All right, so here's basic algebra. And then 4 divided by 16, n equals 4. So what's the value of n? N's going to be 4 because I just solved for that equation, and that's how we do that. Is such a compound aromatic? Well, for B, there's a big question mark here. It is aromatic if it's a ring, if it has an odd number of bonds, if it is flat, right? That's what these things are all about. So this one I'm kind of wishy-washy on unless I get more details of the structure, because I have to meet all 4 definitions, right? So this we have to answer with a question mark, okay? There are 9 pairs, so this is an odd. That is odd right there, right? 9 pairs. So it meets that definition for aromaticity. But the other three that we've been working with, folks, I really don't know. The problem doesn't really tell me. So because of that, I just have to put a question mark here and say, it could, or it might not be, depending on what else comes along with this particular type of structure. And this question just doesn't give me the details that I need to have to make that decision. All right. So what I'm working in here, if you're trying to follow along in a textbook, is really chapter 8, which is a chapter that we talked about in Orgo 1, but I'm kind of ripping out sections of that chapter, and I'm going into that chapter with a little bit more detail. So if you want to know where I'm at this point, I'm in chapter 8 in section 18. And this is going to be more on aromatic criteria. So what they're going to do is they're going to say, okay, we just gave you these 4 rules. Look how simple. And then they're going to turn around and say, oh, and by the way, here are some nasty exceptions for you to deal with. Okay, so let's see what these exceptions are. Is this aromatic? All right, so this is an easy one. I'm going to say, nope. Okay, well, why isn't it aromatic? Because here is a 5-membered ring. It's a ring, ding, ding. Okay, number 2, does it have an odd number of double bonds? There's only 2 there. It's not an odd number. So because of that, this is not an aromatic. So that was pretty easy. And then they're going to turn around and they're going to give me something like this. Oh, gosh. They give me a positive? How am I supposed to deal with this positive? It seems like that's always the problem that people have. How do I deal with the charges in these structures? So here's the 5-membered ring, and there's a double, single, double. So it looks like this is an sp2, and 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 this carbon down here? What about that one that has a positive charge? Okay, well, the question is, does this carbon have electrons in a p orbit? This is not a typical carbon. This is a carbon that has 3 bonds. There is a bond to a carbon, and a bond to another carbon, and a bond to a hydrogen, and then the bond that was there, that was the 4th one, probably to another hydrogen, that was ripped away. And electrons were ripped away because of that. So remember, I said, okay, here we go. An S was protonated or promoted. Here's our lineup. Here we have 3 bonds. And they're calling this thing an sp2, right? An sp2 carbon. Why? Because, folks, we only have 3 atoms that carbon is at. So here are the 3 atoms right there. 1, 2, 3. There it represents my 3 bonds. So this is a S and a P2 because I've used 2 of those. So I get this kind of weird P orbit that's out there that's still lingering. The problem, though, is that this is a positive. And a positive means that an electron has been removed. Okay, so because there's no electrons in a p orbit, that means it violates the definition. So when I see the carbons like this, and that carbon has a positive on it, well, okay, that means the carbon only has 3 bonds. I've removed electrons from it. Otherwise, it could have had an electron there to promote in a p orbit, and it's not a proper double bond, but it's a p electron, and that's really what this is about. Remember, no, I said that this is going to come back and bite us. So we normally look for double bonds, but the problem here is that when I see these weird little charges, I'm going to have to think about this in a different way. So that positive removed the electrons. We did have something there that could participate, that could have counted. But now the problem is that this was ripped away. That formed this positive carbon, a carbocation, and that does not have any electrons that it can contribute to the delocalized system. Because it's not a true delocalized system, that is not an aromatic. Now, think about what I just said. Because it is not a delocalized ring, That's really what this is about. Back in Orgo 1, we talked about delocalization. And I said, look at this structure. Does it have delocalization? And you would have looked at this structure and said, well, yeah, this one kind of does, because I see a double, single, double cause you trouble. So we know that these electrons could kind of move throughout this entire piece of the molecule. Delocalization is there. It doesn't really go into the corner of the molecule, right? You would have never circled that area and said, yeah, it goes all the way around. No, you wouldn't have. However, some of you might remember the rules and say, well, wait a minute now. This double bond can move toward a positive charge, and that was part of delocalization as well. That is true. That is true. However, the problem is that delocalization can happen, and we do see movement that can go forward like this, but this carbon cannot contribute to that delocalization. This carbon doesn't have electrons to contribute to this whole master plan. And because of that, it does not meet the definition of aromatic. Every carbon has to play a role. Every atom in that ring has to play a role in this delocalization process, meaning it has to have the electrons. Delocalization can go forward. I can get electrons from the double bond that move toward that positive charge. I mean, that was the whole rule of delocalization. The problem, though, is that this is not a contributor. It's just sitting back, and it's just, taking advantage of everything else in the ring. It's like, this relative that never leaves your basement, and they just sit down there and they don't do anything, and they just mooch off of everybody. They're not contributing to anything. Well, that's that carbon. You don't want a carbon that lives in your basement. So this is not an aromatic for that reason. All right, next one. What about this one? Okay, well, as you can see down here, ding, ding, yeah, it is aromatic. Okay, so let's talk about why this is an aromatic and the one before was not. So if you look at this, okay, we got a ring, check. That works for the definition of aromatic. And then we go through and we say, okay, is every carbon or every member of the ring have a sp2 or a double bond or pi electrons, right? Okay, so this one's got it, that one's got it, this one's got it, that one's got it. This one might be the question mark. Okay, well, once again, let's kind of look at this carbon and say, all right, so sp, and there's my per motion. Bum, 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 bum. There we go. So it looks like this carbon is attached to one carbon on the left, one carbon to the right, a fourth one or a third one that's hydrogen. So I know that I'm at least getting 3 bonds, and there we go. So this is a sp2. And now the question, look at this charge. That charge is negative. That means there is a set of electrons that are here. So they had 1, and that negative means there is an extra 1 that's there. So that extra 1 is a set, right? It is a pair. And where is that pair located? That pair is on a p orbit. So because of that definition, this does meet the criteria of an aromatic. All of my members of the ring have electrons in a pi orbit or a p orbit. 2 of them, well, 4 of them, 4 of those carbons are pretty easy to pick because there's the full-blown double bonds that are there. This one was the questionable one again, and that is a pair of electrons, and that pair of electrons does donate and contribute to the delocalized system. So here I see a double bond that can move toward a set of electrons that can then move, and that can then move, and this can then move, and we get this entire delocalized network throughout the entire ring with all contributing to the ring. That's the difference here. So if I see positive types of carbons, I really question those, and I say they probably aren't contributing anything at all. And then if I see negatives on these carbons, They are contributing to the ring, and I do want to count them as a set of pi electrons. So if you go back to the definition of an aromatic, what you're going to see, number one, is there a ring? And the answer is yes. Number two, every atom of the ring has to have a p orbital. Well, they do. My carbons involved in the double bond automatically have them. And that carbon with a set of electrons that's negative now, that is another set of electrons that's in the p orbit. So everything has electrons in p orbitals. Number three, is it plain or flat? Well, if you did the structure for this, it will be. And number four, does it have an odd number of double bonds? So you're looking at this and you're saying, okay, well, there's 1 and 2 and there's even. That doesn't match Huckle's rule. But you are forgetting that that pair at the bottom is also classified as a pi set of electrons, which is really what a double bond is. So that is our third double bond. That's how you need to think about that. So there is an odd number that is there, and that odd number does make that be aromatic. Now, the rules that we apply here can also get applied to bigger molecules. So if you look at these other structures that are on your screen right now, we have naphthalene, which is basically smelling like mothballs and keeps snakes away. People spread it in their yard. They crush them up. They spread mothballs all in their yard, and they're going to go, I'm going to keep the snakes away from my yard. But that's really an old wives' tale. It doesn't really happen. I mean, studies have basically thrown out mothballs, and snakes crawl right over them. So that's phony. Don't think about that. Phenanthrene is in the center, and this is a pretty good indicator for us to measure something like iron in drinking water. So this is an indicator. It's a colored solution. It's a nice purpley reddish color, and then crysine on the end. So if you take a look at these three compounds are all aromatic. All right, so how do I know that? Well, first, let's just look at naphthalene. This is a ring, and this is a ring structure. So these ring structures, yeah, there's a ring in place. Second, is every carbon having a pi set of electrons? So this one has a double, that one has a double, this one has a double, that one has a double, this one has a double, that one has a double. This one's got a double, this one's got a double, that one's got a double, this one's got a double. So yeah, they do. And then do they have an odd number? So if I look at this, there's 1 double bond, 2 double bond, 3 double bond, 4 double bond, 5 double bonds. So the answer to that is yes, it does. And then if you did the structure with a model kit, you would see that this is also a flat molecule. So it meets all 4 definitions or components for the definition of an aromatic. Phenanthrene in the center, same deal, same concept. They're all rings, right? They're multiple rings, but they're all rings. And then if I look at all the carbons, sp2, 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 sp2. This one, sp2, 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 sp2. They all work. And then up here, that's an sp2. This is sp2, sp2, sp2. So they all work and they all meet that definition. So that's a check mark. And then the next one is Huckle's rule. Is there an odd number? So I look at the structure and there's 1 double bond, 2 double bond, 3 double bond, 4 double bond, 5 double bond, 6 double bond, 7 double bond. So the answer to that one is yes, it meets that as well. And then if you made the molecule or if you put the structure into a computer model, it will show you a completely flat molecule that comes along with it. And crysine, folks, is the same way. I think if you see naphthalene and phenanthrene, I think that crysine is going to be similar. So I think that you'll be okay with that one. All right, so let's take a look at another example. This question says, which compound in each set is aromatic? Okay, so what they want me to do is here's set A and there's set B. So it looks like maybe one of these out of the 3 choices that they give me is going to be an aromatic, and I've got to figure out which one it is. Okay, so if I look at the first one in the first set, cyclopropene. Okay, so cyclo, ring, prop, 3 carbons, 1, 2, 3, ene, double bond. There's my double bond. So if I look at this structure, I'm going to say, is it a ring? Ding, ding, that works. And then I'm going to say, does every carbon have an sp2? And then this one's got it, this one's got it, this one, there's nothing there. So this is not an aromatic because of that reason. Now, oh gosh, I've got these two structures, and one's got a positive and one's got a negative, and I don't know which one to do. Okay, so let's just go through and talk about the definitions again. So number one, is it a ring? Yes and yes. So they both meet that definition. Number two, is everything sp2? Right? Is everything sp2? So I look at this and I go, okay, so here and here and here. So I definitely know those up there are. And then here and here, I definitely know that those are. So the questionable ones are down here at the very bottom. So with this particular type of carbon, as we already saw with the positive piece, it is a sp2 carbon, right? It is an sp2 carbon. And this one is also an sp2 carbon. The difference is that they meet that definition, but the next definition of aromatic talks about having everything contribute and having an odd number when you do it. All right, so as I go through and I take a look at the second one back here, it looks like an odd number of double bonds is not going to happen here with cyclopropenyl anion. The reason is that this is a double bond up at the top, and then this one is also a contributor. So because of that, this doesn't quite meet the definition of an aromatic, because this gives me an even number of double bonds, and I can't have that. When I go to this middle one, I look at this middle one and I say, okay, it is a ring. All of the carbons here are sp2. Right? This one has 3 bonds. It's got an empty shell, but it's got 3 bonds. So it is an sp2 carbon. And then the next one is Huckle's rule. And Huckle's rule basically says you need an odd number. So I do only have an odd number, and that's that one there. So this one is an aromatic in this case. All right? Now, I know we like to have all of the carbons contribute here. But here we see something slightly a little different, just basically due to the ring structure that is formed here. It's a 3-membered ring, and what we've kind of seen before are 6-membered rings, basically. That's what we've been doing. All right, so let's take a look at B. B, we go through the definition. B says, okay, you need a ring. Well, all 3 of these are rings. Okay, so I know that's not going to be the deciding factor. The next one is everything's got to be sp2s. Everything. So I automatically look at this carbon here, and there's no double bond on it, and there's no charges on it. So that one's not an aromatic. I already know that. And then I look at my other 2 options, and I see those other 2 options, and I go, okay, well, these are kind of tricky. So I need to kind of stop and think about what's happening here. So this one, that carbon, is a sp2 carbon. And this carbon is a sp2 carbon. The difference is that the p orbit here doesn't have electrons, and the p orbit here does have electrons. Okay, that is the difference between these 2 structures. This has the electrons removed, which is why they're positive, and this has an extra electron, which is why it's negative. So both of those meet that part of the definition. They are all sp2s all the way around. The next part is, do they have a set of pi electrons that they can contribute to this ring and make it fully delocalized with an odd number? That's the thing here, an odd number. So if I look at the cycloheptatrionyl cation, what I'm going to find out is that this carbon does not contribute any electrons. Well, this one has a bond, this one's got a bond, and this one has a bond. So there's 3 sets of pi electrons in this structure, right? And then here to the right-hand side, I see those pairs of electrons right there. So this one has a bond and a second bond and a third bond. And because that's a set of electrons in a pi orbit, this set of electrons, it does count. So this will be 4 sets. And folks, we can't have an even number. We have to have an odd number. So that one does not work. So yet again, this positive structure, because this was the untraditional kind of 7-membered ring, this kind of changes things, and we just have to go in order of an aromatic definition to figure this thing out. So number 3 meets all criteria. The first one gets ruled out because that carbon is not sp2, and the third one gets ruled out because it gives me an even number of pi sets of electrons. The same thing happened with number A. Number A was ruled out because this carbon, that was not sp2. And then the last one was ruled out because this carbon was negative, and that was a set of electrons, and this gave me 2 sets of pi electrons. And it cannot be even. It has to be odd. So the middle pieces right here are the ones that are aromatic by the definition. Now, there's something else that I want to throw in here. We're going to talk about this in a little bit more detail somewhat later, but these were pretty close, weren't they? It met all of the definitions except for Huckle's rule. That is the one that it did not meet. It met all the others, right? The sp2 carbons, the ring systems, it met all the others. But it did not meet Huckle's rule. It violated that one rule. This is what we call an anti-aromatic compound. That is that proper definition. So if everything looks good according to plan, check, 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 and then we get to that Huckle's rule, and we have a compound that violates Huckle's rule, and that's the only one it violated. That's the only one it violated was the Huckle's rule. This is what we call an anti-aromatic compound. If that rule was fixed, then it would be aromatic. But because of that, it's not an aromatic, and we call it anti-aromatic. Okay, well, that's the only rule that can be violated, folks. That's it, just the Huckle's rule. If it violates the ring, we don't call that anti-aromatic. It's just not aromatic, okay? If it violates this sp2 type of carbons or sp2 members of the ring, we don't call that anti-aromatic either. That's just not aromatic. Only if Huckle's rule is violated, the proper term that's used is anti-aromatic there. All right? So that's where section 819 is going to take us. So again, if you're following in your book, flip to chapter 8, section 19, and this is where we're going to be picking up in the next video, and we'll flesh this out. Well, I'll go ahead and flesh it out now because it's pretty easy. We've already really talked about it. Just like aromatics, it's one rule that's getting violated. Huckle's rule is the one that we cannot talk about, that we cannot meet. And if Huckle's rule is violated but everything else is a-okay, we have a anti-aromatic compound. They are reactive. They are unstable. They are not fully delocalized. And that's what contributes to the way that they behave in a reaction scheme. So anti-aromatics, folks, there's your definition. Now, the other term is a non-aromatic or not aromatic. And again, that violates other things rather than Huckle's rule. Again, is it a straight chain? If it's a straight chain molecule, then it's going to violate rule number 1 that says it's got to be a ring. So that is going to be classified as not aromatic. Simple, just like that. Not aromatic. But if it meets everything and it only violates Huckle's rule, and that's it, just Huckle's rule, then this is going to be a non-aromatic compound. All right, so in the next video, what we will talk about is Chapter 8, Section 20, and we're going to talk about heterocyclics. So the reason that I'm giving you these reference points, I normally don't do this, but the reason I'm giving you the reference points is because I am somewhat skipping around in the text, and I'm pulling sections from random chapters that need to be fit together to make a full-blown aromatic and benzene type of lecture. So that's where this material is going to be coming from up next. If you need to go to your textbook and read more about it, kind of brush up on it, maybe you didn't understand something in lecture when I talked about it, that's perfectly okay, but this is going to be your reference point. So chapter 8 is where we're working in. Again, different points of reference, different chapters are going to be used throughout this lecture, especially in the very beginning, and this is my way just to kind of say, hey, if you need to go back and get a reference, this is where you're going to find this information. It's scattered around, and because of that, I'm giving you that reference point. So next video, we'll talk about heterocyclates. I'll be here waiting, so when you come back, I'll be ready to gab, probably for another 30 minutes. I'll see you then.